Good morning. Good morning, class. Good morning, all.
Morning, sir.
Yeah. Henry, you're welcome. Please, Dr. Henry, can you please mute? Okay, thank you. Today, we hope to conclude the topic we've been having. We've been dealing with for over a week. International correlation with matter. Today, we are basically going to be looking at the attenuation of X-ray and gamma ray. It's a follow-up to the interaction of radiation with matter. So in all the types of photon interaction with matter, the Rayleigh scattering, the Compton scattering, the photoelectric effect, pair production, triplet production, and even photo disintegration, they all lead to one thing, which is the reduction in energy of the photon. Of course, that is plausible. When photons interact with matter, because of the various processes they pass through as they move from one section of the tissue to the other, they lose energy via excitation, ionization, and um, the radiative and losses when they interact with the nucleus of the atom. In a sense, we say they have been attenuated. That is, they have lost some of their energy. In fact, this is the most important aspect of medical imaging. If they don't undergo attenuation, then we wouldn't be able to have different, we wouldn't be able to have imaging, because imaging is actually as a result of the attenuation of these photons with matter. Different materials have different attenuation coefficients, and even if you are talking about the same material, even if they have the same density, they have everything the same. But if the imaging, if the interaction occurs at a different depth, of course, that introduces a variable. So in all this we have said so far, we are talking about, we are one way or the other looking at attenuation. And attenuation is as a result of both scattering and absorption. Some of the photons will be absorbed. They eventually lose all their energy to the surrounding atom, while some will continue. They will lose some part of their energy and continue moving, like Compton scattering and Rayleigh. Though Rayleigh is a form of scattering, doesn't essentially lose any of the energy. That is, the outgoing photon or the scattered photon has essentially the same thing as the incoming photon. So we have to look at some of these attenuations that are relevant in the radiology. The first one we'll be looking at is the linear attenuation coefficient. Attenuation coefficient. if we have, if you have a particular observer, of course, in radioactivity in our secondary school days, we're told alpha rays can be stopped in air. When alpha ray travels in air, it just needs to travel a few millimeters in air before it is stopped. Beta ray can be stopped in air, but it has to go a very, very long distance. But essentially, if you have a piece of paper, that can effectively stop beta ray. But for gamma ray or for X-ray, that is not the case. It travels far, far wide. Far, far into any tissue it encounters. So you have to have a very, very thick tissue for it to be stopped. If it is in air, it can travel millions, billions of miles, kilometers before it eventually loses its energy and comes to rest. So we are going to look at that. So and as they are traveling, they are losing energy. Some photons are removed, some go through. So we can actually characterize the number of photons lost, or the number of photons removed, or the amount of energy removed over the existing energy. You can associate the thickness delta X directly proportional to the amount of photon removed. That is, the thickness of an absorber is directly proportional to the number of photons removed. That is, a smaller thickness of material will remove a smaller amount, but a bigger thickness of material will remove a bigger amount of a particular radiation. This time around, we're talking about X-ray and gamma ray. So with that, we can actually introduce a constant of proportionality. Mu n. This mu is a linear attenuation coefficient. It describes the amount of thickness that will be required to remove a certain amount of X-ray or gamma radiation. So in that case, we can just write so this is an attenuation coefficient, a linear So this is a linear attenuation coefficient. So that's it. This is a linear attenuation coefficient, which is a measure of the amount of thickness that will this amount of thickness to remove a particular amount, a particular number of X-ray photon. We use this a lot. It's used a lot in attenuation. Is used a lot in radiography. For example, you have a different material. You want to know the amount of thickness that will remove a particular amount of radiation. So in that case, for example, if you want to look at if you have some material that, of course, have a different contrast, we want to look at the energy that will give us the best contrast. And the energy that will do that is directly proportional to the linear attenuation coefficient. So you might have after drawing your graph, because some K edges, L edges, and so on and so forth. You have different material. This material, at a point in time, you have when you have this to be very, very great. If you have the difference to be very, very great, you can now maximize. This is energy. Let's say you're looking at a 50 electron volt. Let's say you have a maximal amount of difference at this energy. So you just make sure you image at that particular energy, to give the best contrast. So that is one of the application of linear attenuation coefficient. In fact, that is the major application of the linear attenuation coefficient. So at times when you're given for questions, the quiz will be sent to you maybe today. So that before and then okay, it will be sent today. So we have, for example, you have at a particular energy, maybe at 80 keV, you have that we're looking at the two. I'm looking at a 2 millimeter. Will reduce maybe maybe 1,000 photons. Reduce 1,000 photons to maybe 800 photons. After this is the original amount of photon. This is the remaining amount. So it means 200 photons have been removed. So in that case, mu will simply be 2 mm over n over n, 200 over 1,000. Now n is 1,000 initial, 1,000 over 200. I hope I'm correct with this equation. Let's see. Sorry. So I made a mistake. The equation should be this way. The number of the photon removed is directly proportional to the thickness. Sorry, it's the other way around. The number of photons removed, I've been looking at this. The number of photons removed is directly proportional to the thickness of the material. So we now have introduced our proportionality constant n over n. We now be okay. This is it. So this is still a linear attenuation coefficient. Sorry about that. At the end of the day, we will have this mu to be equal to n over n. So the units for linear attenuation coefficient is per centimeter, or per millimeter, as the case may be. Because this one and this one, they will cancel out. They are dimensionless. So in our case, for this one that we were given before, our mu, our linear attenuation coefficient will now be equal to, the number removed is 8,200. That is 200 over the original amount, 1,000 multiplied by 2 millimeters. 2 times 2 millimeters times 2 millimeters. So at the end of the day, we have 0. Okay, 2 over 2, 2, 2. And then we have a 0.1 per millimeter. This is just an illustration. So for this particular X-ray or this particular gamma, the attenuation at 80, the mean attenuation coefficient at 80 millimeter, at 80 keV, sorry, is 0.1 per millimeter. Of course, it is different at different energy. In the table of linear attenuation coefficient, you have maybe at 20 keV, you have the list of linear attenuation coefficient, and so on and so forth. So this is basically what happens. And you should know that this linear attenuation coefficient is the contribution of all the whatever we have been talking about. In the diagnostic energy range, the linear attenuation coefficient is linear attenuation coefficient, the total linear attenuation coefficient, the total linear attenuation coefficient. The total linear attenuation coefficient is the linear attenuation coefficient as a result of Rayleigh scattering, as a result of Compton scattering, as a result of photoelectric effects, and so on and so forth. Then, of course, if for high energies, we can also add that of cell production. And then triplets can also follow suit. Okay, we don't deal with such energies regularly. So this one is enough for us. The total linear attenuation coefficient is a result of the contributions of all these things. So in the material, all these things, they will actually have a contributory pattern. So that is why we have a different values for the linear attenuation coefficient at different energy, because at different energies, the contributions of each of these will vary. So the linear attenuation coefficient that we have used, that is linear attenuation coefficient we have used this value or this equation cannot only applies to very, very small thickness. That is a very, very small thickness of absorber. If we have very great thickness, maybe something like a 6 centimeter, 10 centimeter, and so on and so forth, this equation becomes invalid. It's no longer valid. Because if you want to make it valid, you have to divide such that thickness to very, very, very small material. So you have this big thickness. You have to divide it into very, very small slices of very, very small thickness to have to make this make it relevant. I mean, to make it correct or to make it applicable. That is small. But if in doing that, we are moving into a differential equation, which we don't need. You can imagine somebody just sitting down to be dividing this, of course, and doing it mathematically, analyzing it mathematically. But it's going to be much more time consuming. So instead of doing that, we use calculus in finding and in going about this. And it reduces to the calculus at the end of the day has an equation, has a solution which is constant, which is correct for any type of thickness, which is n naught is remaining n epsilon minus that is, you have so this is this is the initial number of X-ray or gamma ray. At the end of the day, you see, this is similar to this. This value here is similar to this. So this one we can derive this equation from here again for very, very small delta x. We can actually derive this equation. So this is the more general equation we can use for any thickness of absorber we so encounter. So, but one thing we should note is this N is for photon removed. This N is for photon removed. Photon removed. While this one is for photon transmitted. Photon transmitted. We shouldn't make that a mistake. Why this N stands for photon removed? This N stands for photon transmitted. So if you want to get this one, the photon removed, you just subtract this from this. So our N here, our N is simply N naught minus N. So that to give us a photon removed from here. Because the amount transmitted is simply the initial amount minus the amount removed. So we shouldn't make, there shouldn't be any, we shouldn't have problems with that. So this is one of the, of course, linear attenuation coefficient reduces with energy. It reduces with energy. Linear attenuation coefficient reduces with energy. And of course, we have different portions of linear attenuation. We have that due to Compton scattering. You can draw the different graphs for them. But for this is just the general linear attenuation coefficient. So we, and of course, this is a measure of, it has a direct relationship with the density. The higher the density of the material, of course, the more packing the materials we have. Hence, the more the linear attenuation coefficient. You can imagine material whose packing is like this. You have the atom spread out this way. You can compare it to another material in which the atoms are much more together. They are tightly packed, closely packed. When a photon is coming in, it will interact more. There will be much more interaction of this photon. Hence, more of the photons will be removed. As against this. This will allow the passage of more photons. So the density of the material has a very, very significant contribution to linear attenuation coefficient. So let's quickly go to mass attenuation coefficient. It's also one of the very, very useful attenuator. Attenuation and description, mass. The linear attenuation coefficient, density plays a major role, and it is used when we are 23. And it is used when we are looking at when we are comparing a linear, when we are comparing different materials. When we are comparing different materials, that is, how is this material different from this other material? But if you are looking at a particular material, for example, soft tissue, or let's say water, and you want to see how much the energy of the photon is removed, you're not looking at the amount of, or you don't want to base it on the density of the material, because of course, different materials can have different density. But if you're looking at the same material, how much energy, how much photon is removed from a particular beam, how much a photon is removed when it traverses a particular material, then linear attenuation coefficient is no longer useful. We bring in a term called mass attenuation coefficient. And mass attenuation coefficient, of course, doesn't depend on density, because we are talking about a particular material. So mass attenuation coefficient is simply linear attenuation coefficient all over density. So linear attenuation coefficient all over density just helps us to describe the mass attenuation coefficient of the material. Because for example, if you look at water has three different states. So they are going to have a constant mass attenuation coefficient. So it means that mass attenuation coefficient of water, liquid water, is something as mass attenuation coefficient of ice, is something as the mass attenuation coefficient of what's it called? Steam, because we have we have assumed that all these have the same different densities. So essentially, the densities are not the same. Essentially, not the same. But just for convenience sake, we have normalized all their density to unity. So in that case, if you want to look at this, I want to look at the same material, we use mass attenuation coefficient. But of course, this one's we have just used as this as an illustration. Film is different from ice and ice is different from liquid. But we are talking about the water. It's the same water we are talking about. So mass attenuation coefficient is that. And the unit for mass attenuation coefficient is centimeters squared per gram. Centimeters squared per gram. As against that of the linear attenuation coefficient, which is per centimeter. If you can actually get that, if you divide per centimeter all over density, density is in gram per centimeter cube. That's another unit of it instead of kilogram per meter cube. And then again, we're going to have a centimeter per. Because if you bring gram per centimeter cube, not that we have centimeter cube remaining, centimeter square remaining all over gram. So centimeter square per gram is the unit for mass attenuation coefficient. So those are the relevant attenuation and coefficient we're going to have. We have so many others which we don't need to bother you with. So we want to look at other very, very important terms that we use in one of them is HVL. HVL is half value layer. Layer. It's just the thickness of material that will reduce the radiation or reduce the energy of the radiation or they reduce the number of photons by 1/2. If you're able to achieve that, that thickness of material is the HVL of that photon beam at that energy. How am I saying? As if you have a thickness of material, you have a photon coming in. And so you have 4 photons. If at the end of the day, you have 2 photons escaping or being transmitted, this thickness of material, let's say 2 millimeter of copper, whatever, is the HVL of that energy, maybe 70 keV. So 2 millimeter of copper is the HVL for this energy of photon. So it is the amount of the material that will reduce the radiation energy, or reduce the number of photons interacting with that material by 1/2, which is 1/2. So it is a measure of the energy of a measure of the photon energy. It's a measure of the photon energy. And at times, of course, that's the quality. If you're talking about the quality of the photon, we talk it in terms of, or we'll speak about it in terms of the HVL. So that is why the HVL is one of the HVL tests is one of the most important tests in radiography. If you don't have appropriate HVL, or I mean, if you don't have a particular value of HVL, a particular modality, then it is not safe, because you begin to have some unwanted energy moving into the patient, which don't contribute to image quality. Just they just end up overdosing the patient. So HDL test is, in fact, the most important. Yeah, most important test that has to be performed in terms of radiation protection of the patient, and of course, every other person using that facility, the radiographer, the radiologist, yeah, the risk of causing scattered and photon. So HDL is very, very important. So if you have, you can have so many HDLs, one HDL, two HDL. You have one thickness of material here, another thickness of material. Assuming these are HDLs, you have 40 photons. This one reduces it by, I want to have 20 will go through here. At the end of the day, 10 will go through here. 40 will remain 20, 20 will go through, and will be, and they have 5. So 5 over 40 will be the amount remaining, which is 1 over 8, which is a 1 over 8. And 1 over 8 is simply 1 all over 2 raised to power 3. That is 1 over 8. So the number of HGLs is simply the number remaining from the initial value is simply 1 over 2 all over n. Where n is the number of HGLs. Okay, 7 minutes. Yeah, n is the number of HGLs. For here, in here we have 3 HGLs. 3 HGLs. So at the end of the day, the number remaining is a 1 over 8. And you can simply do that by saying 1 over 2, which is the HGL, or which is the half, okay, HGL, yeah, 1 over 2 all over n. Assuming we have 10 here, this is 1 over 2 raised to power 10 to give us the amount of photons that will be remaining. And of course, the number that has been reduced has been removed. This is 1 over 8 of the total forever. We have we solve examples, running questions, and then to make the matter to simpler. So HGL is a measure of the quality of the beam measure. And of course, we are not dealing with a monoenergetic beam, we are dealing with a polyenergetic beam. So the half value is actually the measure of the energy, the average energy of the polyenergetic beam, because it's not monoenergetic. Like it is monoenergetic, it is simple. So calculating the HGL is very, very simple. You look at that energy, and then we get the HGL. But for X-ray, it is a different. So because we are dealing with polyenergetic beam, it is useful. We talk about the effective energy. This is another thing very important. The effective energy of the beam. You have the beam, which consists of different energies. Let's say the heater has been able to remove some portion of the beam, maybe from 1 keV to around 20 keV, 30 keV. Of course, we're not mammography. We don't need so low energy. So the effective energy is actually the energy that is a representative of, or we can say it is the mean energy of the X-ray beam or the gamma ray. Effective energy, it is a measure of it is the mean energy of the beam. Because you can have beam after a filter has been applied, it moves 0, let's say 1 to 30 keV. The remaining one from 70 to maybe 120, if you're operating at 120, you just have a mean. You can have a mean which is around 80 or 90 keV. So this 90 keV is the effective energy of the beam. So it is an estimate of the penetrating power of the beam. An estimate of the penetrating power of the beam. How much the beam can penetrate is measured by this effective energy. Of course, it also has it has a link with the HVL. The more the HVL, I mean, the more the effective energy, the more the HVL you will use. You can't compare the HVL of 90 keV to the HVL of 60 keV. This one will have a higher HVL because it has it is the effective energy which we are looking at as 90 will require um, much more thickness of the material to reduce it on one half. So effective energy is a measure of the penetrative ability or the penetration of that energy of that X-ray beam. The higher the energy, the higher the material required to bring it to one half. We can also talk about the mean free path. Mean free path. During our earlier discussion on the international relations with contact, we mentioned during the introductory aspects, the introduction, we looked at the some distances we normally calculate in these interactions. We looked at the range. We also looked at the path. This time around, we're looking at by mean free path, we're looking at the average distance a photon travels in tissue. It can range from 0 to infinity. Okay, it can run from 0 to infinity. Looking at the time we have 2 less than 2 minutes more. It can run from 0 to infinity. So we can begin to calculate at this point is 0, at this point it is 2 centimeters, at this point it is 100. All we need to know is all we need to do is just calculate the mean free path. That is the average distance a photon traverses a matter, and it is 1 minute. And it is MFP is actually 1 all over mu, 1 all over linear attenuation coefficient. So if you know the linear attenuation coefficient, you can actually get the mean free path. So we also need to look at the beam hardening. Beam hardening. As photon traverses matter. 1 minute, less than 1 minute. As photon, okay. You can join in. I want to quickly end this now and then start immediately. Okay. I'm ending.